Okay, I'm experimenting here with our take-up of the graphing questions. So if I look at this first function that I've given you to graph, to figure out the domain, I'm looking at the values of x that would make the denominator here equal to 0. And if x is equal to -3, that denominator is equal to 0, and we know we can't divide by 0. Never divide by 0. If you do, you will be sad. So we have the restriction on our domain that x cannot equal -3. And there's nothing to reduce that with, so that infers that this is a vertical asymptote of x equals -3, which you'll notice I've dotted in on my graph already. I also noticed that the degree of the numerator is bigger than the degree of the denominator. Sorry, equal to the degree of the denominator. So if I have 3x over x plus 3, I'm looking at the coefficients of the leading coefficient of each of those numerators and the denominators to be able to come up with my equation for my horizontal asymptote. So my leading coefficient of the numerator is the 3, and the leading coefficient of the denominator is the 1 in front of this x, and 3 divided by 1 gives you 3. So that's where I came up with y equals 3 as our horizontal asymptote. Now for an x-intercept, we let y equal 0. When I multiply both sides of this equation with an x plus 3, I end up eliminating that denominator on the right-hand side, but 0 times x plus 3 will just equal 0 on the left, so we end up with 3x equaling 0, which gives us x equals 0. So we actually have an x and y intercept both at 0, 0. Similarly, for the y-intercept, you could let x equal 0, but you're still going to get 0. So I also then plotted the point 0, 0 on my graph. Now, I get into the derivative stuff. So normally when we were in advanced functions, we'd have to check the end behaviors as x approaches -infinity, as x approaches -3 from the left, and as x approaches -3 from the right, and then as x approaches positive infinity. Yuck. We can now use our calculus for this. So I took the first derivative of my function. I've got the derivative of the top, which is 3, times the bottom, which is x plus 3, minus the derivative of the bottom, which is 1, times the top, which is 3x. And then that's all over the bottom squared. And I just leave that in its factored form of x plus 3 all to the exponent of 2. I've expanded and simplified here. And then I ended up with 9 over x plus 3 squared. Now, this line right here is just for me, for reference for when I do the second derivative later on. For my critical numbers, I'm going to let that first derivative equal 0 and solve for x. Now, here's where the experiment comes in. I'm going to see if I can move this. Oh, I can. Yay! All right, I can move this up so we can see the rest that's coming down the pipe here. I ended up with my first derivative, 9 over x plus 3, all to the exponent of 2, equaling 0. I multiply both sides by x plus 3 squared, eliminates it, and I get an untrue statement of 0 equals 9. It's untrue. We have no solution here for x. So when we check the intervals of increase and decrease, the only thing we're using here are our places where our domain is not defined. Those will be places where our function is not differentiable. I find that my function will be increasing on both of those intervals. Then I took my second derivative. I used my function, my simplified function that I have up here, and I did the derivative of the top, which is 0, times the bottom, minus the derivative of the bottom, which is 2x plus 6, times the top, all over the bottom squared. I then simplified that, set that equal to 0 to find possible points of inflection, and I again get no solution. So then I checked my concavity for that, and I found that when x is less than -3, I was having a function that was, my function was concave up, and when x is greater than -3, my function is concave down. So then, when I put all those pieces of information into my graph, you can see I am concave up when x is less than -3, and my function is increasing. If I look at this section down here, my function is still increasing, but you can see that the function is concave down there. So hopefully that helps you understand how to do the first graph. All right, here we are with our second graph. Again, I'm looking at where my denominator is equal to 0, and I'm noticing that my denominator would be equal to 0 when x equals -3 once again. Okay, but this time I can reduce, so that gives me a whole at x equals -3, and my reduced form is this. From what I know in advanced functions, that is just going to give me a line that looks like y equals x take away 1, so a y-intercept of -1 and a slope of +1. There is no vertical asymptote in this case. There's a whole at x equals -3, but no vertical asymptote there. There's also no horizontal or oblique asymptote because, again, the simplified form takes us to what looks like a linear relationship there. For my x and y intercepts, I've calculated those by letting x equal 0 and y equal 0 for the alternate ones, and I get 1, 0 as my x-intercept and 0, -1 as my y-intercept. So I could graph some information based on what I have so far. Now, just so that you know how the calculus fits in, because this is actually a simple one to graph from advanced functions, if I were to do the derivative, I ended up with my derivative equaling 1. Now, I could do my derivative from my original function right here, which came from the derivative of the top times the bottom minus the derivative of the bottom times the top all over the bottom squared. That actually results in the very same derivative as taking the derivative of the simplified function here. Now for critical numbers, I'm going to set that derivative g at x equal to 0, and again I get 0 equals 1, which has no solution, just like I had in the last example there. Intervals of increase and decrease, I'm going to use the values around my whole instead of around the vertical asymptote. So we end up with positive again, and my function is strictly increasing, so that fits in with the calculus. If I try to do the second derivative is just equal to 0, and 0 equals 0, which is always true, but it really gives us nothing about concavity, because if I put my second derivative equals 0, it's neither positive nor negative, so I'm really not talking about concave up or concave down. There's really no information here about concavity. I've gotten the coordinates of the whole. I've plotted the whole. I should have labeled that here as a -3, -4. And I've graphed that as my line, and it is a strictly increasing function as my first derivative suggested here. All right, moving to the last example. All right, for example C, when we look at the domain, there's no value of x that's going to make that denominator equal to 0. It's always going to be 4 or bigger. No matter what value you put in for x, when you square it, you're either going to get 0 or a larger number from there. So our domain is just all real numbers, and that means we also have no vertical asymptote for this particular rational function. The degree of the numerator is smaller than the degree of the denominator, which makes then the horizontal asymptote y equals 0. And here I've solved for my x and y intercepts. I only found one intersection point overall, and that's at the origin. My first derivative, when I calculated the first derivative, I took the derivative of the top, which is 5, times the bottom, minus the derivative of the bottom, which is 2x, times the top, all over the bottom squared. And then I simplified that and got this as my derivative value here. Now I do have my expanded and simplified form over here so that it would help me with the second derivative when I got there. I'm going to work with the factored form though when I find my critical numbers. And for my critical numbers, I let y prime equal 0 here, and I solve that. Multiplying both sides by the denominator will eliminate the denominator, and then I divided both sides by -5 and got this line, which means x is equal to positive or -2 when we square root. We have both the positive and the negative number. I've checked for my intervals of increase and decrease with my table here, and this is my behavior of y on this line. So I found there was a local min at x equals -2 and a local max at x equals 2. They turn out to be absolute maxes and mins actually for this graph. I've also calculated my y coordinates here. So you can take a look at the y coordinates. That will help me plot these points here and here on my graph. Plus I already have my y-intercept and x-intercept at 0, 0. All right, looking at the second derivative now. So I used the form down here. The derivative of the top was the minus 10x times the bottom minus the derivative of the bottom times the top all over the bottom squared. Now I left this kind of in factored form to see if there was anything I could common factor, but there wasn't. So I just expanded and simplified and ended up with this, which then I worked at factoring that numerator so that when I set my derivative, my second derivative equal to 0, I've got the factors here. And what I've done is I've multiplied both sides of the equation after I set it equal to 0 by the denominator to eliminate that. And I end up with my 3 possible points of inflection, one at 0, 0, one at positive 3.46, and one at negative 3.46. So the other one has no solution there. I checked for my intervals of a concavity, and I calculated the y-coordinate of the point of inflection at, whoops, this should say negative 3.46. I had made a mistake earlier. If you could see, I erased a bunch of stuff. So thanks to Cam for pointing that out to me so I could fix it. And then I plotted my points of inflection here. Probably not quite at the right spots in terms of position on the graph, just based on if I had a scale or whatever there, but it's close. So you can see that my graph is concave down here, concave down for this section. If I just switch my color, I am concave up for this section. We switch to concave down again for this section, and then we move back to concave up for that section. So it fits my intervals of increase and decrease. It also fits my concavity.